Hello everyone. Welcome to our presentation about excluding the irrelevant, focusing reinforcement learning through continuous action masking. My name is Roland Stolz, and this project was a collaboration with my colleagues from TUM and UC Berkeley. In reinforcement learning, an agent often explores a vast action space, but not all actions are equally relevant in every situation. However, given a certain control task, we often have prior knowledge about actions that are potentially useless, unreasonable, or even dangerous. Consider the scenario for autonomous driving. The ego vehicle, controlled by the agent, drives past a construction site on the left. We know that steering to the left is potentially unsafe in this scenario and should therefore be avoided. Additionally, there can be interdependencies between the actions. For example, the larger the acceleration, the smaller the steering angle should be to avoid unstable driving. Using this task knowledge, we can define an explicit set of relevant actions which the agent is allowed to explore. For discrete action spaces, this concept is well established, and we now extend this idea to continuous actions. Our approach for continuous action masking restricts the actions selected by the policy to the set of relevant actions AR. We achieve this by transforming the original policy distribution into the relevant policy PyR, which has the property that all actions sampled from it are contained in the set of relevant actions. We require two assumptions for our approaches to this concept. First, the relevant action set is convex and can be computed in every state. And second, since we are working with probability distributions, the employed RL algorithm must use stochastic policies, which are typically Gaussian distributions. We propose three approaches for obtaining this relevant policy. The ray mask transforms actions sampled from the original policy distribution by scaling them along a ray, which stretches from the center of the relevant action set to its boundary. This transformation yields actions that effectively represent samples from the relevant policy distribution. The generator mask uses a zonotope, which is a set representation that projects a hypercube onto the lower dimensional action space. We define the original policy distribution in the space of the hypercube, which ensures that after the zonotope mapping, all sampled actions are contained in the relevant action set. For the distributional mask, the relevant policy distribution is the original distribution, just truncated to the relevant action set. We sample from the resulting truncated distribution using geometric random walks. Also, a big part of our work is to derive the effect of these three masking approaches on the policy gradient. You can find the details of the derivation in our paper. We integrated our approaches into PPO and tested their effectiveness across 4 control tasks. We compared our methods to standard PPO and to an alternative approach called action replacement, which substitutes actions outside the relevant action set with ones sampled from inside. We look at 2 quadrotor stabilization tasks in both 2D and 3D environments. The seeker environment is a simple reach-avoid task where the agent tries to reach a goal while avoiding an obstacle in a 2D plane. The Walker 2D experiment uses the Mujoko Walker 2D environment with a cumulative power limitation on the actions. In all 4 environments, our masking approaches show better sample efficiency and performance compared to the baseline and in most cases to the replacement approach. Notably, in the Walker 2D and 3D quadrotor experiment, the baseline PPO algorithm fails to learn an effective policy, which is likely because the relevant action set is small compared to all possible actions. To summarize, by enforcing hard constraints on the action space of the RL agent, action masking can incorporate domain knowledge and thereby improve sample efficiency and convergence speed. Additionally, action masking can not only improve safety, but by utilizing the appropriate relevant action sets, it can provide actual safety guarantees. In the future, we want to extend continuous action masking to deterministic policy algorithms such as TD3 and to handle relevant action sets that are non-convex, disjoint, or even both. Please reach out to us if you have any questions, and thank you very much for your attention.